Welcome to our community service series in How Computers Work. I'm Elder Stanley, a missionary for the Church of Jesus Christ of Latter-day Saints.
Hi, I'm Austin Kellum. I'm a student of Elder Stanley here.
This time we're discussing machine language programming. With the simple computer that we've been talking about, we don't have capability to do high-level programming language, but we want to learn about, with a simple machine, how you actually write machine language programs at the level of the processor itself. So we talked last time about how we're going to use this 4-instruction virtual machine my student built for my computer, so we don't see all the digital logic, but we're just going to concentrate on how we could put together instructions to make various programs work. We saw several of them last time. Here's the one that we talked about that shows different kinds of pictures: circle, square, triangle. We have a place here where we see the accumulator. This also shows the instruction that's pointed to by the program counter, what it is. And we'll see here the memory. We'll be able to load a memory image, and we can actually edit the memory and change contents in the memory. So it uses exactly the same memory file as my little computer uses. So these are the commands, again, that my little computer understands. It's got an add command. The operation code for add was 0. So if we see a 0 for the first character in the display, like right here, we don't see 042, but this needs to be a 3-digit number, so there's really a 0 there. If we have a 0 in an instruction, that says add the number that's in the accumulator to the memory, to a number that's in memory, that's at the address that the rest of the instruction gives. We have a load command. What the load command does is takes a number from the memory and puts it into the accumulator. We have a store command. The store command takes what's in the accumulator and puts it into the memory. And then we have a jump conditional command. What that does is takes the address that's given in the instruction and puts it into the program counter. The way in this little computer, the way we can tell what the program counter is pointing to is we'll see a highlighted line. And so that's the one that the program counter is pointing to. If we say jump to 0, then we should see that highlighted line move up here. So that's the program counter. We also have input and output instructions. These use the same opcodes as the load and store, but if we say load from FF, the highest address, rather than use the memory address, what we'll do is we'll grab an input from the keyboard. If we give the command to FF, store FF, then instead of storing the instruction into memory, or the data into memory, we'll put it on the display. So we send one character at a time to the display. Instructions are 3 hexadecimal digits. The operation is the first digit, and it's a 0 to 3, indicating whether it's an add, load, store, or jump. So those are the options for the first character in the instruction. The next 2 digits go from 00 to FF. And what that is the address we're going to load from, the address we're going to get a number from to add to the accumulator, the address we're going to store to. If we have a jump command, it'll be the address where we want to run the next instruction from. Again, if we have load and store with FF as the address, then we'll actually load from the keyboard or right to the display. Here's some examples. So 005 would say, add the number that's in memory location 5 to the accumulator. 231 says, copy the number that's in memory location 13 to the accumulator. 2 1, 2 would say, load a copy of the number that's in the accumulator to memory location 21. So I think this one actually grabs a number that's in memory location, puts it in the accumulator. This takes what's in the accumulator and puts it in a memory location. 300 would say if the accumulator is not 0, start executing the next instruction at memory location 00. 1FF says stop the computer until a character is typed on the keyboard, load that character into the accumulator, and then continue executing. So here's that very simple program we looked at a little bit last time about converting a number from uppercase to lowercase. So in this case, the whole program is written down here. The 1FF says get a character from the keyboard and put it into the accumulator. The 2FF says send the character in the accumulator to the display. 005 says add what's at memory location 5 to the accumulator. 2FF says display the number that's we now have in the accumulator. It should be the lowercase character because we've added 20 to that character. And now we have a 300. That says jump up here to the top and get another character. So this is programmed. This first 5 characters or memory address, memory data are instructions. In memory location 5 is a 20. That's not an instruction, that's data. That's what we're adding to the character that we get from memory. Let's go look at this one in our little emulated computer. So we'll come over here, we're going to say load memory file. We're going to load echo and make lowercase. So here's that program in memory. Let's single step through the program. So right now you can see that the first address is highlighted. That's where the program counter is pointing. What this tells us what that instruction that's at that location is. It says get a character from the console, get an input from the keyboard. So that's single step. We now see the input light up right here, so we can type in a character there. I'm going to put in an uppercase A. And now we were paused until we typed a character. Now we can do the next instruction. If we say do that, now we see the A in the display. That was our display command. Right now we have a 41 in the accumulator. That's the character for a capital A. We're going to add to that value in the accumulator the thing that's in memory location 5, which is that 20 hexadecimal. So what will this be after we add 20 to it?
61.
Yeah, 61. So we'll do that step. Now the accumulator says 61. Now what are we going to do in this next instruction? 2FF. Send the accumulator to the display. So let's do that. Now we see a lowercase a up there. And now the next instruction says jump to 0 if the accumulator is not 0. And the accumulator isn't 0, it's 61. If it were 0, it wouldn't do that instruction. It would just continue on. So let's single step. Now you see the blue lines back up there at memory address 0. So we're ready to do another character. Let's put in a capital Z. Oh, I guess I didn't single step, so it wasn't ready to take in an input. We'll put a capital Z, and now we're ready to display that character. Here's the character for a capital Z, 5A. When we single step, we add 20 to that. Now we got 7A instead of 5A. Then we display that 7A, and now we've got a lowercase z, and now we're going to jump to the beginning. Let's see if we can go in here and edit this. I'm going to come down here to where this memory location 20 is, memory content 20. Let's make that 1 instead of 20 and see what that does, okay? So we'll come back up here and stop editing the memory. And now we have exactly the same program, but we've changed that data from 20 to 1. So what do you think will happen now when we add 1 to a character?
I don't know.
Let's
What will
find
happen?
out. So a single step says enter a character. I'm going to put in a capital A again. So we've got a 41. Now we're going to add, instead of 20, we're going to add a 1. So now when we actually do this instruction, now it's 42 in the accumulator.
No, it's going to be a capital B.
Yeah, so now we see a capital B. Then we go to 300, we jump back up to the top, single step, and we're back there again. Okay, so that's one program. Feel like we understand that one?
Complicated, but yeah.
Yeah, so anyway, these are the machine instructions. They're the instructions that this computer absolutely understands. Let's go back to our PowerPoint presentation, a very simple program. This is a table, it's called ASCII character codes in hexadecimal. So this shows us what those characters are stored like in the computer, you know, in a hexadecimal code, what each of those characters look like. I probably should have brought a pointer here so we could look at these easier, but the first 2 lines are what we call control characters. They're things that don't really have a character that you see. Those are things like a tab. What does a tab character look like? We know what it does, right? It tabs over, but what does a character look like if you put it in text? Or a backspace, or a line feed, form feed, carriage return, line feed. We'll use this one later on. But anyway, those are what we call control characters. And then if we want to see what a character is, like capital A, you see that that's on the row with a 4 on the front. You want to point to that 4?
4.
So 4, 1. So a capital A would be 41 hexadecimal. A lowercase a would be 61, 6, 1. Number 1 is 31. Okay, so these are called the ASCII character codes, and those are what we're using in our programs. Okay, when we wanted to, let's say we looked at that calculator program that says 1 plus 1 equals 2. This is how we would design that program. What would we want to do? If we want, this is the example of what we want. 1 plus 2 equals 3. 3 plus 3 equals 6. So we want to write a program that'll do that. What we have to do is read in a number, then display the number. So we read in a 1, display it. And then we want to display a plus sign. We want to read in a second number, display an equal sign, display the sum of the numbers, and then advance to the new line so we can do a new one. So that's our calculator program we want to try to build. Let's see what we would have to do that. Now, one of the things that's kind of important, if you look at those ASCII character codes, you'll see that the code for a number 1 is not 1, or the code for 0 is not 0. It's 31 or 30, 31, 32, 33. So, because of that, if we read in like a number 1, which is 31, and then we read in a 32, which is 32, we add those together, we get a 63, which would be a lowercase c, not the number 3. So what we're going to have to do if we want to actually do a calculator is we have to convert a character from a number, or from a character to a number. The way we do that is we subtract the character 0 from that character. For example, if we enter a 1, a 31, if we subtract the character for 0, which is 30, we'll get a 1. Or 2 is 32. If we subtract 30, we get 2. But our computer only adds. So what do we do if we want to subtract 30?
You add 30 instead.
Yeah, we have to add a negative number, right?
Yeah.
So it turns out the negative of a 30 in a 10-bit number is 3D0. So what we're going to do is add a 3D0 to our number that we get. One of the other things that's kind of important is we're going to use the accumulator to print a plus sign and other things. That means we're going to have to save that number because we can only have one thing at a time in the accumulator. So let's see how this program looks. So this is a program to add two numbers, this calculator program. So the first step we're going to have is get a character. That's a 1FF. 2FF is display that character. And then we want to do an add. So 011 is add the character that's at memory address 11. So in memory address 11 we have this 3D0. That's our negative 0. So we add that. That converts the number from a character into a number, from 0 to 9. So we add that negative value, and then we have to save it in computer memory. So we're going to save it as in memory location 15. Now we load memory 12 into the accumulator. This is a 2B. Turns out a 2B is a plus sign, so we're going to load a plus sign into the accumulator. We'll display the accumulator value, the plus sign. Then we're going to get our next character. That's a 1F. 2F, display that character. Now we need to save, add the save number to that. So we're going to say 015. We're adding the number that's in location 15 to that number, and that will create a character that is whatever that digit is plus the character that we just got. And then we're going to display that character, so that's our answer. Let's see, do we want to do that?
You stop
Load.
here.
Okay, add the save number. Save the memory in memory location 16. So we're going to add the displayed character to our number. We don't want to display it there. We want to have an equal sign first. So we're going to save that in memory location 16. And then we're going to load 13 into memory. That's the equal sign. Display that character, so that'll display our equal sign. Then we're going to load memory location 16 into the accumulator. That's this number that we saved, the answer. Display that character. Load location 14 into the accumulator. Display that. This is a new line character, so that'll take us to the new line so that we'll be on another line, so we're not overriding things. And then we want to jump to the start and do another line. So that's our program. Let's go over and look at that one in our little computer. Stop. So we'll load here, memory file. Load memory file. We're going to, this is called a formatted add two numbers. So here's those instructions. So let's start running this program. We'll, I guess I don't have a really good way to just clear the display. Maybe what we should do is start this again. So this is for instruction virtual machine. Let's load this formatted add to a number command. So now we'll just single step through it while we see what it does.
Yeah. Just do it. Single step.
Okay. So now it's waiting for a character. What one should we type?
2.
2. Okay. So here's the 32 in the accumulator. And now the next instruction is going to be add that negative 0 to it, the 3D 0. We haven't done that yet, but when we do single step, now what's in the accumulator? Well, we typed in a 2. This is now, instead of a character 2, it's a number 2. Now what we're going to do is we're going to save that to memory location 15. So that's that number 2. Then we're going to display that value. I guess now we're loading in from location 12, and that was our plus sign. And then we display it. So there's our plus sign. We're going to load. I guess we're asking for another input. What should we put in this time?
Let's put in 5.
5. We'll display that character 5. We're going to add to that 5 character a 2. So that's like when we typed in 5 with a +2.
Yeah.
Then we'll go 5, 6, 7. So it should be a character 7. We don't have to convert them both to characters and then convert it to numbers and then convert it back to a character. We just converted one to a number, then we can add it to a character and it'll do the right thing. So now what we should see when we single step here, we should see that character that's our answer. Oh, I guess we haven't finished this yet. So here's a 37. So that's our what's in this memory location 16. So we've saved our character that we want to display down there. Now we're gonna
Display.
yeah, gonna load a equal sign, and then we're going to
Display the answer.
display the equal sign. Yeah, and we're gonna load in our character that we saved from memory location 16.
There's a 7 right there.
Yeah, so that's our 7 that we
2
loaded
plus
up
5
in
is
there.
7.
And now we're going to display load the character to go to the next line and display it. And so what that does is actually moves us to the next line. Then we're going to jump to the top and do it again. So now we can put in another one. We'll just tell it to run now. So we can put in a number. Let's put in 1 plus 1 equals 2. What do you think happens if I push 5 plus 5?
You'll get a 1.
Plus 5. So what happens here is, if we look at our ASCII table, we'll see what this is doing. Let's go back here. So we put 5 plus 5, so what's 10? Well, it turns out there's digits 0 to 9. If we did have a 10 character, that's what it would be a colon, so that's what we got. Okay. Here's another program we'll look at. This one's called Hello World. We could do a program where we say load an H, display H, load an E, display E, load an L, display L, load another L, display L, load an E or O, display O, hello world, and write that all out. But that wouldn't be very exciting. In computer science, we usually like to figure out some way to have a loop.
Yeah.
A lot of times there are commands that you have that make it so that you can set a pointer to various values and increment that pointer. In this little computer, we'd only have the 4 instructions, so that's a little harder to do. So I had to do something here that's a little bit, I don't know, a computer science professor might say is shady, because what I'm doing is I'm changing my program as I execute it. But it turns out in this von Neumann architecture, the instructions, the data, all of those are the same in the computer memory. So what we do is we load a character. It's actually the first character of our hello. So we load from memory location B into the accumulator. We send that to the display. Then we've got an H on our display.
Then it says load command address 5, which is 10B.
Yeah, so this would normally load that same character. But what we want to do is load the next character. So we load that load command into the accumulator. We add 1 to it. So now it's going to say 10C.
Yeah.
So we'll load from memory location C. We save that back into memory location 5. And now we run that command. So that command will get the character at C and send it to the display. And then instead of jumping back to 0, 0, because we're not going to want to use that 10B character again, it's kind of out of date. So we jump back to memory location 1 if the accumulator is not 0. And then we keep running through here. So what this does is means we can print out a string like hello, and when we want to stop, all we have to do is load 0 into the accumulator, And then when we do the jump to memory location 301, it will say, oops, the accumulator's not 0. So then it'll come down here. And this is an input command that causes it to pause until we type in something. So there's our hello world program. So let's load this one into our little computer and we'll see how it works.
I got 1 minute left.
Okay, well, we're pressing on. So let's load here, program file, hello world. I guess again we got this problem.
It's all right.
Yeah, we'll just run it, okay. Let's tell it to run. So it says hello world, hello universe. So what it's done is it's loaded successively a whole bunch of characters into memory. You see down here, there's a whole bunch of numbers that are the data that's getting loaded, the hello world, the hello universe, the codes for all of those letters. And we end down here with a 0, and that tells it to stop running. So now it's trying to do an input. So anyway, that's a hello world command program. Usually when we write machine language, we write like this. If we go to a little bit higher level, we'll do what's called assembly language. In assembly language, the instructions are exactly the same as the machine language, but we'll let the computer do some decoding for us. So in this case, we don't have all the memory addresses there and have to tell it what memory address to go to. We can say, go to the right location, go to the last command location. You know, here's the number 1 where it's located in memory. Here's a hello. And we can put in a string like this rather than having to write in those individual characters. We can just say, hello world. So anyway, that's called assembly language. We could talk about machine language as level 0 in programming languages. Assembly language is like level 1. High-level languages like C# and Pascal and Python and Java, those are all other, you know, higher-level languages. Anyway, we've got a summary here. Let's try to go through the summary really fast. Computers use binary to simplify the electronics and the math. The fundamental logic gates and/or a NOT can be used to make all the other logic devices in a circuit. Computers are programmable machines that take instructions from memory and process them one by one. We change the instructions, we change what the computer does. Computer processes billions of instructions each second. While commercial processor systems are millions of times more complex than my 4-instruction computer, the principles are the same. And I appreciate this opportunity to share this with you and the